Water circulates throughout a house in a hot water heating system. The water is pumped at a speed of 0.5 meters per second through a 4 centimeter diameter pipe. In the basement, under a pressure of 3 times 10 to the 5th pascals, that pipe leads to another 2.6 centimeter diameter pipe on the second floor, 5 meters above. So we've got several different things going on in this problem. So the easiest thing to do is just go and draw a picture of this pipe going from the basement to the top, and these two different points in the pipe, which we'll call point 1 and point 2, let's just start labeling everything that we know. So at point 1, which is in the basement, we know that the speed, which we'll call V1, is 0.5 meters per second. We know that the diameter is 4 centimeters, which means the radius is 2 centimeters, or 0.02 meters. So R1 is 0.02. And we know the pressure, so P1 is 3 times 10 to the 5th pascals. And that looks like about everything for the bottom portion of the pipe. So at the top, we know that the diameter is 2.6 centimeters, which means the radius is 1.3 centimeters, or 0.013 meters. We know that the height, the H2, is 5 meters, which means we can actually go back down here and say the height 1 is 0 meters. And we know that looks like about all that we know. And you want to figure out what is the water flow speed in the part of the pipe on the second floor. So the first thing we're trying to figure out is, what does V2 equal? There are two equations for fluid flow. One is the equation of continuity, which is simply the equation A1V1 equals A2V2, and the other one is Bernoulli's equation. That's the much longer, more complicated one. So in this case, since we know something about the area for both parts of the pipe, because we know the radius at the top and at the bottom, and because we know the speed at the bottom, we can solve for the speed at the top just using that simple equation. So we can write down for part A that A1V1 equals A2V2, and if you plug in the formulas for the cross-sectional area, since it's a circular pipe, we can just write down pi R1 squared V1 equals pi R2 squared V2. We have a pi on both sides, which cancels out, and we can solve for the V2 simply by dividing both sides by R2 squared, so that those will cancel out. So V2 is equal to R1 squared, which is 0.02 squared, times V1, which was given as 0.5, divided by R2 squared, which was 0.013 squared, and that is equal to 1.18 meters per second. And that should make sense to keep the volume flow rate constant, that because the radius is smaller at this part of the pipe than down here, the speed should be higher than it was down here. Moving into part B, we now want to find the pressure in that part of the pipe. So we're now looking for the P2. The only equation for fluid flow that has pressure in it is Bernoulli's equation, so I'll just start by writing that long equation. P1, that's capital P1, plus 1/2 rho V1 squared plus rho G H1 is equal to P2 plus 1/2 rho V2 squared plus rho G H2. And the first thing we can do is focus on the fact that the H1 is equal to 0, so we'll just knock that term out of the equation. We're trying to solve for the P2, so we want to get that by itself. So I'll bring these other terms over to this side of the equation, which would give you P2 equals, and it's going to be P1 plus 1/2 rho V1 squared minus the 1/2 rho V2 squared. I'm just going to factor out the 1/2 rho and just make that a 1/2 rho quantity V1 squared minus V2 squared, and then minus rho G H2. And if you plug all of these numbers in, the pressure at point 1 was 3 times 10 to the 5th plus 1/2 times the density of water, which is just 1,000, times V1 squared, that's 0.5 squared, minus V2 squared, which we solved for in part A, that's 1.18 squared, minus rho, again, is 1,000, times G, which is 9.8, times the height, which was 5. Plug all of that in, and you get a pressure equal to approximately 2.5 times 10 to the 5th pascals.